Hello, this is a presentation on differential power analysis with Sasebo-w. The topic is mass AES implementation. Before talking about the topic, we'd like to recapture what we did in previous session. We already have software for DPA attack, but it is in first order. The order represents number of points to analyze at a time. All DPA attacks focus on intermediate values to analyze the data, and the task mass AES do is to mask all these values. To be able to implement a mask AES, we'd like to be familiarized with the algorithm AES. AES stands for Advanced Encryption Standard. Here is the algorithm flowchart. We could see that the standard seems quite complicated, which was designed to prevent attackers from revealing the secret key. We are analyzing step by step. AES run consists of 3 steps: add run key, substitute byte, shift rows. Before all these operations, we define an array named state, which we are storing all our intermediate values. Also, we'd like to substitute XOR operation with add for later presentation. Add run key basically adds secret key and plain text to our state array. Subbyte use icebox of 256 arrays to substitute multiple bytes to create nonlinear I/O operation. Shift rows shift kth row to the left by k-1 as explained in this chart. Next, mix column. We could see that for each element in column, new state value equals XOR sum of other 3 elements and 2 times itself and next element. This operation actually adds in quite some amount of complexity, but still requires us to mask later as it has some amount of linearity. Then key expansion. Before going through the procedure, we'd like to define a round constant equal to 1 as required by the algorithm. After the first round, the algorithm wished to change the secret key so that attackers could not retrieve more information after the first round. We could see that we are adding icebox of k13 and run constant to key 1, icebox of k14 to key 2, and icebox of k15 to key 3, etc. Other keys just add the keys just made by index of -4. For example, k4 add just made k0, etc. And after runtime execution, run constant equal to 2 times the original run constant. Having been clear about the algorithm, we wish to proceed to implementing CAD software as it was not given by manufacturer. This will also help us for later work on mask AES implementation. To do so, we need to understand the APDU command, at least the ones we use. If we remember, APDU stands for Application Protocol Data Unit. As we are only using 3 commands, we should implement these 3 for standard data communication. Make AES key. PC will send command in byte order of hexadecimal 80, 12, 0, 0, 10, and send 16 bytes of secret key. If there was a response from the board of 2 bytes, 90 and 0, it means command executes successfully. Definitely, the board needs to really set the key with function AES set key 128 key for our case before the response. Similarly, CAD should be able to receive command of 80, 4, 4, 0, 10, and 16 bytes of data of plain text. Then pull up voltage of trigger signal, execute encryption function, stop triggering, and give a response of 9F10 to encrypt given plain text. To get response, what was different was that the data of ciphertext should be sent from CAD to PC followed by response of successful execution. We could definitely make more commands for other algorithms for interest. While in our project, we are mainly focusing on AES algorithm and 3 commands were sufficient. If you burn your hex file into your card successfully and your VCP checker could help you check that you have same result between hardware value and software value, it means implementation was correct. There's no way for you to debug on this system. If you wish, you will have to buy a set of AVR debugger with 80MB163 development board. Without these tools, being careful and making commands of functions and command in your code is the key. As I already implemented standard AES software to cut successfully, I will assume all listeners here have done the same and wish to proceed to implement a mask AES. What is masking? Masking actually means showing something which was not the fact for protection. For example, bigger clothes could mask our fat belly. In our masking protection, we are going to mask every key value and state value, which means we are not giving any way for attacker to retrieve information from intermediate values. There are Boolean masking and arithmetic masking. As we are using 8-bit microcontroller and meeting time constraint was important, we are choosing Boolean masking for simplicity, but with sufficient effect. Instead of guessing how we should do it, I'm introducing the way of doing it and then consider how it should be done. These are the requirements. The key should be masked with min for masking and mask_out for cancelling output mask. In first round of operation, state array should be added with mask_out to cancel out first round's output mask in the key. After add round key operation, as mask_out cancels out itself, we could see we only got min in the mask. We would like to require to have a new SBox for byte substitution operation to mask equation to make equation new SBox of value with min equals old SBox of old value plus mout. We are not displaying why, we are using it because we need it. Then shift rows, as mout was equally added to every element in the state. There was no change in mask. Then we are doing remasking. Our remasking was to cancel out mout and add in mask for mixed column. After mixed column, we are getting mask out. Thus, we could see that everything could be cancelled out at last, but all intermediate values are changed. Basically, there are two sets of mask. min in the key and mout after mask SBox. Mask in state array after remasking and become mask out after mixed column, as mixed column was not pure linear function. With this way of masking, execution was simpler. What we need but don't have are min, mout, mask, and mask out. Among these, min and mout could be generated with random number function. Then we could easily calculate mask SBox by defining a new SBox and use for loop to create by SBox m of I XOR min equals SBox of I XOR mout. Similarly, mask for mixed column operation could be calculated with random number function, and we can calculate mask out by applying mixed column function to the mask. Now, after knowing how we should do work, we came to think why we need to do remasking. Well, without introducing a new mask, we have to cancel mout for correctness of the step mixed column. However, when doing so, there is leakage of information to attacker and they could easily attack by applying first-order DPA analysis. With mask before mixed column, we could make sure that each and every intermediate value was masked. Now, having implemented mask AES and cut successfully, we wish to apply a first-order DPA attack with 1000 power traces to see the effect of masking. In our case, correct key should be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. However, from the result of this attack, we could see that none of the key guess was correct. Compared to previous attack with 300 traces, maximum correlation here relates to a wrong key with much smaller correlation. This means that our implementation of mask AES masks intermediate values and protect the card from first-order DPA attack successfully. In conclusion, first-order DPA attack could not attack mask AES, and this may lead to our next topic, multi-order DPA attack.